Hello, my name is Marco Huber from Fraunhofer Institute for Computer Graphics Research, IGD, in Darmstadt, Germany, and I will present on behalf of my colleagues NT Lu, Philipp Terhörst, and Naser our work Efficient Explainable Face Verification based on Similarity Score Argument Backpropagation. Automated face recognition has become an increasingly important part of our lives. It can be used to unlock a smartphone, cross borders, or even to pay with your face. However, the methods based on deep learning have the disadvantage of being difficult to understand because they include millions of parameters and are highly complex models. The reason or clues why two face images are determined to be a match or non-match by a system has received increasing attention recently, especially in security-related areas, but also for usability. It is interesting to understand why two images are falsely recognized as a match or falsely recognized as a non-match. For example, the question, why didn't I match my passport at the automatic border control gate? A current trend is to follow a black box approach, where only the input is changed extensively and the changes in the output is observed. Without a deeper understanding of the inner working of the model, this approach to get insights how the model is working is also time-consuming. In our paper, we propose a training-free explainable face recognition approach, XAP, that is competitive with state-of-the-art on several different face recognition models while being also time efficient. We also propose the first explainable face recognition benchmark, patch LFW, including an evaluation protocol that allows to compare explainable face recognition approaches in an objective manner, and we also compare our proposed approach with different state-of-the-art solutions. In our approach, we propose to backpropagate the similarity score of a face image pair through a Siamese face recognition setup to efficiently indicate which parts of the image pair contributes to a match or non-match decision. By investigating the positive and negative impact of feature dimensions on the similarity-based comparison score, gradients based on these impacts can be backpropagated to highlight important pixels. An overview of our method is shown on this slide. In the first step, we propagate both images through a Siamese network of face recognition model M to gain feature embeddings of the face images. We extend the face recognition model M to M bar by adding a cosine similarity layer, which calculates and outputs the cosine similarity of both input faces to include the matching process in the network architecture. The weights from the embedding layer to the cosine layer are derived from the face embeddings. Given the cosine similarity function, we can observe that the cosine similarity will increase if the feature values in the feature dimension share the same direction, and otherwise the score will be decreased. Since the final decision of a matching or non-matching decision is not just dependent on the similarity score itself, but also includes the system-dependent decision threshold, we include this information of this calculation also in our approach. With the assumption that each feature in the different feature dimensions ideally at least contributes equally to the matching decision and therefore to the similarity score, we define an argument threshold as an equal share of the system decisions threshold for each feature dimension. Based on this argument threshold, we now decide for each feature dimension if it is a positive argument by reaching the argument threshold or a negative argument if it is below the threshold. For each feature dimension, we therefore decide if the features contribute to the matching decision or not. We then calculate the gradients based on the arguments, either only for the set of positive arguments or only for the set of negative arguments. We calculate the gradients backwards through the face recognition model to obtain the pixels that have the most influence on the positive or negative arguments given both images. The gradient maps we obtain by this to indicate which pixels had the largest impact on the positive or negative arguments. In the final step, the gradient maps are processed by taking the mean of the color channels and merging the positive similarity and the negative dissimilarity map into a single map by subtracting the negative map from the positive map. To show the generalizability of our approach, we utilize 4 different state-of-the-art face recognition models in our experiments. All models share the same ResNet 100 architecture and have been trained with the corresponding loss functions. All the models were trained on the MS 1 million version 2 dataset, and the used models are ArcFace, Elastic Face Arc, Elastic Face COS, and Curricular Face. and they are all used as pre-trained models provided by their respective official repositories. We utilize these models to show that our approach can be applied to a wide range of diverse face recognition models without training or fine-tuning. We also compare our approach in terms of quality and latency with two state-of-the-art solutions, XCOS and XFace. XCOS provides a weight map as well as a patch cosine map, while XFace provides three different variations of their approach. For the evaluation of the proposed explainable face matching approach and the comparison with other methods, we built a new benchmark dataset, PatchLFW. PatchLFW is based on the labeled Faces in the Wild LFW dataset. Since in most cases it is more interesting from a practical perspective to know why the system made a wrong decision than to understand why it made the right decision, we artificially increase the errors that the system makes. To do this, we increase the amount of false non-matches by adding on the matching pairs patches from a random image of a different identity. To synthetically increase the amount of false matches, in each of the non-matching pairs, patches from the same image have been added to the reference image. And in total, we randomly added 27 patches of size 16 × 16 pixels, which may overlap on the images or on the reference image. Given this new PatchLFW dataset, the false match rate as well as the false non-match rate at a fixed threshold determined on the equal error rate threshold using the whole LFW dataset increased dramatically as shown in the table, which was our goal. And now a well-suited explainable face matching approach should be able to identify and highlight the added patch areas, as these are the clues or reasons why the wrong decision, the wrong matching or wrong non-matching decision has been made by the system. To evaluate the quality of explanation maps in a quantitative way, we evaluate on our newly proposed PatchLFW with a novel evaluation method called Decision-Based Patch Replacement, DPR. The DPR curves are inspired by insertion and deletion curves. Based on the decision of the patched image pair, the patched images are adjusted. Either the identified most similar or the identified least similar pixels are replaced by the original pixels in an iterative step. The manipulated pairs are then evaluated regarding false match rate and false non-match rate. If the explainability approach is of high quality, it should be then able to detect the areas, the added patches, that lead to false matches and false non-matches, and reduce the errors when more and more pixels are replaced. Here you can see an example of the different explanation maps, but also a visualization of the replacement evaluation. Depending on the similarity or dissimilarity, the most influential pixels are replaced with original pixels from the LFW dataset. We can observe that different areas of the face have been identified as important by the different approaches. Our approach correctly detects the inserted patches at the lower left face side, shortly above the mouth. The results show that on all models and for both errors, our proposed XSAP approach outperforms the random baseline. Our approach shows to be applicable to a wide range of diverse face recognition models. Even though the XFace methods show slightly better performance, they are not as efficient as discussed later. On the ArcFace model, our approach outperforms the pre-trained XCOS-S approach and is comparable to the pre-trained XCOS-W approach while being training-free. To evaluate the efficiency, we perform the computations on the same machine. We use the reference implementations of the respective authors and only consider the time for creating the similarity maps. We select 200 random images from LFW, so in total 100 image pairs. To get as close as possible to a realistic application for an end user, we also evaluate the time for a run and process the pairs in pairs and not batch-wise. The average time needed to create an explanation map, as well as the total time needed to create 100 different ones, is provided in the table on this slide. Our approach is much faster than the other training-free approach, XFace. XCOS is faster than our approach, but has to be trained in advance, which is not represented here and also performs worse than our approach. And with this, I want to conclude my presentation. In our work, we proposed XSAP, an efficient explainable face verification solution, which is based on the backpropagation of similarity score arguments, and we also proposed a novel explainable face recognition benchmark, PatchLFW.